A simple button click. You might think it's just one perfect transition that your controller sees. But the moment you look a little closer, you see this. Not just one transition, right? Well, this little thing called switch bounce has been part of buttons for a very long time. And buttons are almost everywhere. From early doorbells to modern aircraft, from television sets to car dashboards, we have been pressing buttons for decades. So I thought, why not follow the journey of a button click, right from the mechanical switch all the way to how the controller actually handles it. And for that, I'll be using this heavyweight STM32F4 Nucleo board. So let's see what happens behind the scenes when you click a button. Notice that when we press this button, we can actually hear a little clicking sound. Definitely not the sound you want to hear. Yes, that's okay. The most common button type you will come across in embedded systems are these momentary tactile switch kind of thing. I have a few examples sitting right here with me. We have these push buttons on different development boards, tactile button matrix keypad, rubber membrane keypads with those little conductive carbon dots, and even this tiny micro button on my soldering light. They all look quite different mechanically, but electrically, they are all doing the same basic job. Of course, not every button is momentary. There are also latching buttons that stay in their new state until you press them again. But let's stick to the former because it's the one you will encounter the most. So what actually happens inside a tactile button? Beneath the plastic cap is a thin metal dome, almost like a tiny spring diaphragm. When you press the button, that dome bends down and connects two metal contacts, completing the circuit. As soon as you release it, the dome springs back up, breaking the connection. Simple? Not quite. Those metal contacts don't touch each other perfectly in a single instant, and because of their mechanical motion, they actually collide and separate for a few milliseconds before finally settling. That's exactly where the term switch bounce comes from. Now, let me connect the button to a GPIO pin on this STM32 Nucleo board, say PC6. Let me name it BTN. And from this point onward, STM32F446ZE will be our reference microcontroller. The concepts, however, remain same for most controllers in general. Okay, so one of the first thing a microcontroller does after reset is set up its clock. For STM32, the place to look is the reset and clock control RCC section. Now system clock can be generated using HSI, high-speed internal oscillator, HSE, high-speed external crystal, or through the PLL, depending on your application's requirement. In this example though, system clock is set to 168 MHz. Not every peripheral receives this clock directly. The GPIO ports are connected to the AHB1 bus whose clock is derived from the system clock using AHB prescaler, and that is set to 1 here. So GPIO port bus also gets 168 MHz clock. Anyway, even though the clock is available on the bus, GPIO-C is still asleep. Before the CPU can access GPIO-C port, we have to explicitly enable the peripheral clock in RCC. Only then does the hardware power up and allow us to access the pin. Next, suppose PC6 is selected as a simple GPIO input with an internal pull-up resistor. When I open GPIO init function, a quick glance can tell us that individual resistors of this GPIO are getting played with. I won't go into much detail here, but you have the model register where input state is selected for the pin, and in PUPDR register, pull-up gets enabled. Okay, now that we have our button connected, GPIO configured, the obvious question is, how does the microcontroller deal with it? Well, there are two common ways of detecting a button press, polling and interrupts. Let's start with polling. Inside the while loop, let me simply read the button state and check if it has been pulled low, and if it is low, well, let's say the button is pressed. Now, once the button is pressed, let's do something that actually takes some CPU time. For example, I'll send a message over UART. And just to make this a little more obvious, let me throw in another 100 milliseconds delay on top of that. These two lines can basically represent any piece of code that we normally want to execute right after detecting a button press. Let's run it. Open Hercules. Nah, not that one. This one. Alright, let me click the button. And there we go. Pressed message received. Simple, right? Honestly, this is perfectly fine for a lot of applications. If the task we are doing after a press detection takes significantly longer than the transitions, we are naturally going to miss them. But not every application is that forgiving. To demonstrate such a case, whenever button pressed variable gets set, let me simply increment a counter. Incrementing a counter practically takes no time, so it keeps updating itself as long as the button stays in the reset state. For our convenience, I'll even add a UART message that prints this counter value. But there's one important thing here. I'll print the value just once, after we are well clear of the button press condition and the system has returned to its idle state. Let's run it and open Hercules as well as the logic analyzer this time, so we can see what's happening on both the windows. Alright, let me click the button and there we go. Count prints value 125. Nice. From far away, the transition looks absolutely perfect, just like social media influencers. Zooming in, however, we can clearly see the signal bouncing on press and the release side. The entire transition period is roughly 130 milliseconds, and within that period, we have got plenty of highs and lows, some lasting only microseconds and others stretching into milliseconds. This is what the problem is. Right now, our counter is essentially counting throughout the low period, so it gives multiple count from one single press. Now, how do we make this reliable and stick to just one count per physical press? For that, let me add a debounce period, say around 50 milliseconds, and I'll make a small change to our example. What we will do is keep updating our tick counter continuously as long as the button is in the reset or logic low state. The moment the button goes high, the tick counter stops updating. But we also continuously check whether the current tick has moved far enough beyond our last updated tick, specifically by our defined 50 millisecond debounce period. And this is where things get interesting. During the initial press, due to the bounce transitions, this condition never meets. Eventually, the button settles into its stable low region, and here we don't have any significant difference in current and last updated tick. On releasing the button, again smaller bounce transitions don't meet the condition. But once the button finally settles at a stable high and difference between current and last recorded tick exceeds the defined 50 millisecond period, well, that's when we get one real button press. And counter also gets incremented. Let's run it and open the serial monitor. Clicking the button now. And there we go. One click, one count. No matter how the signal looks underneath, we are getting one logical button press out of it. And this is somewhat similar to what I used in my IR remote project built around an AT-Tiny 85. That application only needed to know whether a button was pressed or not to send IR signals. So polling combined with simple debounce worked perfectly fine for it. Now, let's look at another situation. Suppose we are building a menu-driven embedded application. For example, like in my RF fan remote project, a rotary encoder with push button was used to control 16 different fans through a single OLED screen interface. At the same time, the processor would be updating, the OLED screen, handling menu navigation, or working around encoder movement. What if the user presses the button while the CPU is busy doing all of that? That's where interrupts come into the picture to notify you about a press. So let me reconfigure PC6 as an external interrupt EXTI pin. I'll select the falling edge trigger, keep the pull-up exactly as it is, and enable the corresponding NVIC interrupt. And now, instead of a regular GPIO input, our mode changes to IT falling. If we go back and check the GPIO init code, the interrupt configuration part is now active. So now the EXTI ICR configuration register maps EXTI6 to GPIO port C, which means our PC6 pin is now connected to EXTI6. In the interrupt vector table, EXTI9 to 5 interrupt can be seen there in the list along with the settable priority option. Alright, now moving on to the interrupt callback, I'll start with something very simple. Whenever the interrupt occurs, I'll just set button pressed to 1. That's it. Back in the main loop, let's revisit our first use case where the task we are doing takes considerably longer than the button's bounce transitions. So when button pressed is set, I'll send a UART message and add a small delay to simulate some real work. Let's run it. Open the serial monitor, click the button, and there we go. Button pressed, message received. Perfect. But now let's come back to that counter increment case where the task we are doing is actually much faster than the button transition itself. For convenience, I'll again introduce a tick counter along with a UART message that will print only once after all our conditions are satisfied. Let's run this. And this time I'll open the logic analyzer as well so that we can see exactly what's happening at the GPIO level. Alright, let me click the button. Okay, the UART is showing a count of 5. Let's check the actual signal. Okay, so on the press side we have 4 falling edges, and let's also include the falling edge that happens during the release side bounce. Alright, total number of falling edges for this entire transition is indeed 5. Nice. So this tells us that interrupts don't solve switch bounce. They just allow the processor to notice a button event without continuously polling the GPIO pin. Let me now take an example of a MP3 player. Imagine the controller is continuously reading audio data from, say, an SD card and playing music through a speaker. Halfway through the song, you press the play pause button. Now suppose our interrupt callback simply toggles the playback state every time an interrupt occurs. In that case, if we continued like before, a single physical press can generate several edges, and every one of those edges can trigger another interrupt. So instead of getting play and pause, we could end up with something like play, pause, all within just a few milliseconds. And just like that, you end up being a party DJ. Now finally, we want that one physical click should give us exactly one count. So to achieve that, we update our tick count exactly once, right when the falling edge interrupt occurs. Back in the main loop, we check two things. First, has enough time passed since that last tick update, our debounce period, and second, is the pin currently still low. If both these conditions are true, we know we are in that stable reset zone. The tick gets updated just before entering this region, and if the pin is still low after our debounce period, we can safely say, yep, that's a real button press. Let's run it, open the monitor, start clicking. Great, one click, one count. But there's also another way of doing this. Instead of updating the tick only once at the falling edge interrupt, we can keep updating it throughout the entire low period, just like we did in our polling approach. So this time again, during the initial press bounce period, conditions don't line up for a valid press. Then we enter the stable low region where the difference in current and last tick is insignificant. Finally, once the button is released and the signal settles back to high, the difference in current and last updated tick exceeds the debounce period. Once that happens, we have our valid button press. So same as polling, just the detection method has changed. Alright, let's run this version 2. Start clicking, and there we go. It works. Of course, this doesn't have to stop here. You can make the debounce logic as sophisticated as your application needs. For something more complex, you could even bring a finite state machine, FSM, into the picture and explicitly model states like, idle, press detected, debounce, press confirmed. But for our little button here, the journey ends, at least for now. Everything we have discussed so far has been on the software side. Hardware designers often tackle the same problem even before the signal reaches the microcontroller, using filters, Smith triggers, or dedicated debounce circuits. But regardless of whether it's solved in hardware or software, one has to deal with bounce when using buttons in embedded systems. So the next time you use your keyboard, remote, or go to an ATM machine, you will know there's a lot more happening behind that tiny click than meets the eye. That would be it from my side. If you're still here, don't forget to support the channel by subscribing, and yes, do like and share this video. This is Avinashee Tech signing off.